Okay, the next set of trig identities results are what known as the T results, because they all revolve around tan. So we just let the pronumeral T represent tan theta on 2, so half an angle now. So yesterday we looked at double angles, now we're looking at half angles. Then tan theta, because theta would now be double theta on 2, would be 2t on 1 minus t squared. Right? So I can substitute in t for tan theta on 2, and I get 2t on 1 minus t squared. What I can then do is create a right angled triangle, bit of Pythagoras, and we can work out the hypotenuse. Turns out to be, in fact, t squared plus 1. So now I can get a t result for both cosine and sine, just reading off the triangle. So if t is tan theta on 2, then tan theta, as I say, will be 2t on 1 minus t squared. That's just using the double angle result. And then from our triangle, sine theta will be 2t on 1 plus t squared, and cosine theta, 1 minus t squared on 1 plus t squared. But as I say, it doesn't have to be theta and theta on 2. It's all to do with halving the angle. So if t represented tan theta, then tan 2 theta would be 2t on 1 minus t squared. And if t was tan 2 theta, then tan 4 theta would be 2t on 1 minus t squared, and so on. Okay, let's have a look at a couple of examples then. If we've got to show 1 minus cos x on sin x is t, and they'd have to define for us what they want t to be, so t is tan x on 2. So I know I've got to use my t results, so it's just a straight substitution. So x is double x on 2, so I can use my t results for sine, cos, tan, and so on. So 1 minus t squared or 1 plus t squared. The denominator, nicely when we're dealing with cos and sine and fractions, because the denominator is the hypotenuse in both ratios, we're always going to get this lovely situation where we can get rid of it very easily by just multiplying by 1 plus t squared with everything. So when I do that, the top becomes 1 plus t squared minus 1 minus t squared over 2t, 2t squared on 2t, which cancels to just be t. So we're going to use it to simplify this one. We've got 2 tan 75 on 1 plus tan squared. Again, our double angle for tan is 2 tan on 1 minus tan squared. So it would be tempting to simply say tan 2 theta. But they've given us the hint by saying use t results. So if t was tan 75, and then that becomes the t result 2t on 1 plus t squared. So there we go. Then that's the t result for sine. So that must be the sine of theta. Theta in this case would be 150 degrees, double the 75. So sine 150, one of our exact ones, second quadrant, same as 30, so it must be 1/2. Okay, another one to prove. Doesn't actually say use t results, but I guess the fact that they've written tan theta on 2 is a bit of a giveaway. If I use t results, I should be able to show this. So I'm going to let t represent tan theta on 2. Left-hand side, subbing in the t results. Again, the denominators are all 1 plus t squared and everything there. So multiply everything by 1 plus t squared, tidying up the top and tidying up the bottom. 2t squared plus 2t on 2 plus 2t. Actually, that top factorises nicely. And you can see we cancel to get t. That's not my final answer, of course, because they've asked to show it's tan theta on 2. But that's okay, because we said t was tan theta on 2. So indeed, that does equal tan theta on 2. So an HSC one. So again, they told us we're going to use t results. Although it does give us the option, if we wish to, we could do it another method. But usually they're going to tell us the easiest way of doing it. So cosec plus cot is cot theta on 2. Okay, well, cosec plus cot. Cosec, reciprocal of sine. Cot, reciprocal of tan. So it's the upside down of the t results. Denominator both turns out to be 2t in this case. So I can add them quite easily. I just get 2 on 2t, 1 on t. So the reciprocal of t. T was tan theta on 2. Reciprocal of tan is cot. So it actually comes out quite nicely. All right. So we shall do the Shakespeare exercise. Or will we?